guys, this is Academic Chemistry, Chapter 5, Section 2, Arrangement of Electrons, Part 4. So this is the last part on electron configuration, so this is going to be some other little tricks to it. Before we get started with the lesson, I want you to kind of think of a really strange metaphor. So I want you to imagine that there is this vicious bear floating in space. Ah, there he is. Okay, and now I want you to imagine that around that bear, there are these rings of delicious candy, and you're really hungry. And these rings are actually spinning. Now, which of these pieces of candy are you going to try and grab? Are you going to try and grab one that's closest to this bear or maybe on the outside? You know, like I love a good Snickers bar as much as everyone else, but I'm not reaching near that bear. I'm going to go for the Heath bar or something on the very outside because it's further away from, getting mauled to death. Okay, so electrons are kind of like that. Let's talk about why. Okay, so valence electrons. Valence electrons are the electrons found at the highest energy level. So those are the furthest ones out in the electron cloud. They are furthest away from the nucleus. So these electrons are involved in bonding. So when atoms join together to make compounds. So go back to the bear head. When you're another atom, you're going to want to work with electrons to electrons, make your electrons work with another atom's electrons. The electrons you're going to work with are the valence electrons, the outer energy level electrons. You're not going to reach into the inner of an atom to try and make a bond with an electron. That's just weird. There's electrons on the furthest edge of an atom. Those are the ones that are going to interact with other atoms, so they're the really important ones to know about. Let's go over a few elements, their electron configuration, and from that figure out how many valence electrons you have. So beryllium is 1s2, 2s2. So out of these groups, the big numbers, this 1 here and this 2, those are your energy levels, and that means how far away from the nucleus. So the 2s2 is the biggest energy level you have, the second energy level. It's in an s orbital, and there are 2 electrons, so you have 2 valence electrons. How about magnesium? 1s2, 2s2, 2p6, 3s2. So the biggest big number you see is 3. So here are your valence electrons, so you have 2 valence electrons. Calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. 4 is the biggest energy level, so 1, 2, 3, 4 away from the nucleus. There are 2 electrons in there, so this has 2 valence electrons. Now, not everyone has 2 valence electrons, but let's look at something. Where are these on the periodic table? They are all in this group right here. And there's this rule, elements in the same group up and down on the periodic table have the same valence electrons. So anything you see in this group has 2 valence electrons. Let's figure out the rules for the rest of the periodic table so you can make some general ideas of patterns and be able to quickly figure out how many valence electrons an atom has. All right, so how about lithium? So lithium is 1s2, 2s2. So its furthest energy level is 2, and it has 1 electron, so it has 1 valence electron in there. So here's our chart from before. Let's add to it. Lithium is in this group. So anyone up and down here, they all have 1 valence electron. So whether you're hydrogen, sodium, lithium, all of those have 1 valence electron. What about boron? So boron has the electron configuration 1s2, 2s2, 2p1. Out of these big numbers, 2 is our biggest. Notice there are 2 groups as well, 2s2, 2p1. So all of that counts for valence electrons. So you have 2 in your s in the second energy level and 1 in a p subshell, totaling 3 valence electrons. So let's bring back the periodic table from before and add to it. Here, boron is in this group. So anything in this up and down group, all of these have 3 valence electrons. Let's do another one. Carbon, 1s2, 2s2, 2p2. So 2 is the biggest energy level here. I've got 2 in an s subshell and 2 in a p. So we have 4 valence electrons. If you bring back what we had before, carbon is in this group. So all of these have 4 valence electrons. Nitrogen, 1s2, 2s2, 2p3. 2 is the biggest energy level. We are just going straight across, by the way. That's why these are all in the second energy level. So this has 2 in your s subshell, 3 in your p subshell, so 5 valence electrons. So since nitrogen is here, anyone in this group would have 5 valence electrons. Oxygen. So if you go on the furthest energy level out, which for oxygen is the second energy level, you have 2 electrons in an s orbital, making that spherical pattern, and you have 4 electrons in the p orbital, the dumbbell looking pattern. So that's 6 valence electrons. So in an atom of oxygen, the furthest electron in the energy level, there are 6 of them, which means anyone in this group all has 6 valence electrons. Let's do the next one. Fluorine. Fluorine is 1s2, 2s2, 2p5. So the largest energy level for fluorine would be 2. Notice it goes 1, then 2, and both of these are 2. So both are included in the furthest energy level. You've got 2 and 5, totaling 7 valence electrons. So since fluorine makes up this group, which is known as the halogens, all halogens, or anyone fluorine and below, all have 7 valence electrons. So all we have left to talk about now for mapping out on our periodic table is this last group here, and those are our noble gases. And it's no surprise that the noble gases have a little bit of a funny rule. So we're going to start with the smallest noble gas, which would be helium, which is 1s2. So 1 is the only energy level with electrons, so all of the electrons are valence electrons, so 2 valence electrons total. So helium is right here. Notice I'm not boxing in all of our valence electrons because 2 doesn't really fit the pattern. We were expecting 1, 2, 3, 4, 5, 6, 7, 8, right? That's kind of weird. But if you remember from the last lesson, helium actually fits over here for electron patterns. So it's a noble gas because it's full. Helium only has electrons in the first energy level, which only has an s subshell. So it can only have 2 electrons. It doesn't have p subshells in the first energy level to fit those extra 6. So that's the maximum electrons it can have. Versus the rest of the electrons are more like neon. So neon is 1s2, 2s2, 2p6. So it's got 2 electrons in the s subshell and 6 in the p subshell. So out of this whole thing, you have 8 valence electrons. So the rest of your noble gases are going to have 8 valence electrons. When you talk about valence electrons, a term that comes up a lot is an octet. So an octet is having 8 valence electrons. And if you play music, you might have heard of like an octave is 8 notes apart, or if you've taken geometry, an octagon is a polygon with 8 sides. An octopus is an organism in the sea with 8 legs. So oct means 8, and an octet is having a full outer shell of electrons, which is 8 electrons. So our noble gases, these guys over here, are the ones with a full octet of electrons. Later in the chemistry, you're going to learn that everybody wants to be like the noble gases, and they're going to make bonds to be like the noble gases and have a full octet. But for now, we're just talking about plain old atoms, and for now, our noble gases are the only ones with octets. Keep in mind that helium is the exception. It only has 2 valence electrons, but it's still totally full because helium only has electrons in the first energy level, so there's only an s orbital. An s, that spherical orbital, can only hold 2 electrons. In the first energy level, you don't have the p subshell like the rest of the noble gases here all have p subshells. Remember, they fill in this area, so they have 6 extra valence electrons that helium doesn't have. The other thing you need to know is most elements here, these are your transition metals, have 2 valence electrons. There are some exceptions to that rule, but in general, they're going to have 2 valence electrons. One thing you need to know how to do is draw a Lewis dot structure. And these are quick ways of showing valence electrons. Remember that bonds are made with valence electrons, so later we're going to use Lewis dot structures to demonstrate bonding patterns, but right now we're just going to make it basic Lewis dot structures. How you do it is you write the symbol of the element, and then you use dots to represent the valence electrons. And you start on the top and you work your way around. So go to the right, bottom, then left. First fill with 1 dot to show 1 electron. And then once you do all 4 sides, you go back and fill with additional electrons if you have more than 4 valence electrons. So make sure you do a top, a right, a left, a top, a right, a bottom, and a left with just 1, 2, 3, 4. And then if you have 5, 6, 7, 8, you do more. Let's do one together. Aluminum. So Al. If you find that on your periodic table, you'll see it's there underneath boron. So you know it has 3 valence electrons. So here's how you fill. 1, 2, 3. And then that's it. Quickly shows that there's 3 valence electrons, kind of shows for bonding patterns who's available to bond, who's not, and that's it. All right, so using those instructions, I want you to try and draw the Lewis dot structures for sulfur, krypton, boron, and zinc on your own. Find them on the periodic table, figure out how many valence electrons, and then draw your dots. Make sure you're going in that clockwise circle and one per side before you go back and fill again. All right, so hopefully you have done these on your own. Let's start with sulfur. Sulfur has 6 valence electrons, so you always go 1, 2, 3, 4 on their own, and then you can go back and fill again, 5, 6. You'll notice in sulfur you have 2 paired up electrons, 2 paired up electrons, single, single. Krypton. Krypton is a noble gas. It has a full octet, so 1, 2, 3, 4, 5, 6, 7, 8. And now you see why it's so stable. There's nothing available to make any kind of bonds. Boron has 3 valence electrons, 1, 2, 3, and zinc is in that transition metal in the middle, the D block, so go with 2. I want to tell this little story. I want you to imagine that you're sailing in a canoe, and each canoe has 5 seats. So each seat can have 2 people, and you can't share seats until every seat has at least 1 person in it. Like orbitals. So weird. All right, so here's your canoe. And in this story, you have 4 people in your canoe. So is that canoe going to be level? No, it's not. If you notice, there's more people on this side of the canoe than over here, so it's going to kind of be wobbly. All right, now I want you to imagine that there's another canoe next to you, and that canoe only has 1 seat, and it has 2 people. So what can you do to make every canoe balanced and happy so nobody falls over? Well, if you take this guy and put him in the canoe, then, oh, look at that. Everybody's happy. All canoes are even. You might be asking, what does this have to do with electron configuration? Well, there's this rule that we've noticed in atoms that they're most stable when they're either halfway or completely filled. So electrons are going to shift to different energy levels to accommodate this stability. And that's only if it makes a subshell completely or halfway filled, that really stable configuration. Kind of like on your canoes, right? If it was halfway filled canoe, then you had 1 person in each of the 5 orbitals, and then it was totally even. Or if it was a fully filled canoe, obviously then it's all even. This only happens in D block electrons, that middle area, which is those transition metals, or the F block, which are inner transition metals on the very bottom of your periodic table. And that's because of the S subshell that fills right before it. So let's look at chromium. If you do the electron configuration for chromium, you're going to expect it to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And the reason D electrons do something funky is because S fills right before it. S has 1 orbital, so it can have a maximum of 2 electrons. If you lose one of those 2, you're still halfway filled, meaning you're still totally stable. So one of these electrons can actually hop down and go into the atom, into that D electron configuration, and then you end up with this. 1s2, 2s2, 2p6, 3s2, 3p6. Now that's changed, but now you have 4s1, 3d5. So one of the s electrons went into 3d and is now doing a 3d pattern. It takes a little more energy for that electron, but it makes the atom stable and happy, so life is good. All right. Best of luck with electron configuration. Make sure you talk to a teacher if you have any questions. See you in the next video.